essentially, the information or the neuron is activated only if your X transpose alpha is above threshold, right? So next we want to briefly, mention, we call this kind of neural network as feed-forward neural networks. As you know, there are other types of network model as well, right? So the word feed-forward just simply means, all the signals only pass through one direction, right? From our previous example, it's always from bottom to, going up. So you cannot, go back to the lower layers, right? So there's no cycle in the model. So that's what we what we mean by feed forward. Okay. So there, we want to briefly mention, the R implementation. Essentially, you could try these with some simple, structure, right? Simple neural network models, neural net or NNet are packages, and but you could like if you try them, you could tell that if you want to fit multiple layers, it would become very slow. Once your model is larger, so we do not want to pay too much attention for the R implementation, but I think later we will see some Python implementation that is more feasible and much more widely used in current research, right? So so here's a general theory that why neural networks work. So they call it universal approximation theorem. So the idea is just with the unknown fx function, right? With some conditions, right? The point is the neural network model is able to approximate this unknown function sufficiently well, right? The difference would be less than some arbitrary threshold epsilon, and with some conditions on your for example, monotone increasing activation function, right? And for your suitable weights. So these are the model parameters, right? Vi, Wi, Bi, and in computer science literature, they are also called weights, just different names, right? So this theorem, just guarantees some theoretical guarantee that neural network model could work, right? Now, in terms of estimating the parameters, right? People also call them the weights. We want to, introduce some fundamental ideas or algorithms. So as we mentioned, right, the number of parameters. So here we have the +1 is because we also include an intercept term, right? So this is very similar to what we've seen before. But let's see. So it's a much larger number of parameters than, say, in a linear regression, right? So there's a computational challenge. So how do we, estimate all these parameters? So the key idea is something called gradient descent algorithm. Okay, another name is backpropagation. So we want to briefly introduce this idea of gradient descent. as you can tell from the name, right? Oh, as you can tell from the name, this algorithm, you know, is based on the gradient of your objective function, right? So, so first we want to, you know, define the objective, or like the loss that we want to, you know, optimize, right? So for classification, right? For example, you know, the loss can be defined as the deviance, you know, in the following formula, right? So this is essentially saying for each class, right, what is your deviance, and you take the summation. So the objective is, you know, to minimize this deviance, and then similarly, you know, for univariate regression, we are familiar with, you know, the residual sum of square, right? And we want to minimize that. So now we are given the objective function, and then we can introduce, okay, so more generally, right, we can write the objective function as the R denoted by R. And here your theta is the combination of your, you know, alpha and beta parameters. Okay, so theta is just a combination of all of your model parameters. So, and then we assume, right, that your objective function can be, you know, separated for each observation, right, for the ith data point. That is, you know, used for, you know, for subsequent analysis. So this is, you know, an iterative algorithm. Essentially, we want to initiate the theta parameter and then do the update, right? So after initialization, we, you know, calculate the derivatives. In other words, the gradients, right? The gradient of your objective function for all of your samples, right? So by default, right? So because your objective function uses I from 1 to n, so so your derivatives is also, you know, summation from for all the samples, right? But we know that in a lot of a lot of machine learning applications, the sample size n is very large, right? So for n large, this summation would become, you know, computationally too challenging. So people come up with this stochastic gradient descent idea, where, you know, we replace the summation of all n samples by a random subset of the n samples. So, for example, you know, regardless of how large your n is, right, every time, you know, or for each this iteration, we fix, like we call this the batch size, right? We fix a batch size to be, you know, 20 or 30, for example, right? A smaller, much smaller number, so that it is, you know, a random subset of all the samples. Then the calculation of your derivatives would become much faster, right? And so this batch size, you know, is one of the parameters in a neural network model, right? So here's an illustration of gradient descent versus SGD. So on the left, it's gradient descent is, you know, it's easier to understand. Essentially, your optimal data point, right? Let's say your optimal solution is the center of the, objective, right? So all the contours representing the value of your objective function, and towards the center, it is, minimized or optimized, for example, right? And you start from any like any potential points, right? You can start from any, based on your initialization, right? The idea of gradient descent is you find the steepest, the decreasing direction, right? In other words, this direction is orthogonal to the current function that you evaluate, right? So it is orthogonal, at each iteration, and then you take a decreasing direction, right? And so gradient descent can guarantee the convergence, because for each iteration, it optimizes your objective function in the correct direction, right? So that's what the solution path, indicate on the left panel. Then on the right panel, stochastic gradient descent, because every time you do not use all the n samples, right? With a subset of the n samples, you are not guaranteed to, find the optimal direction, right? So that's why we see the purple lines, right? These updates, they are, random in some sense, right? Not necessarily the optimal direction, but, as we cycle through all the samples, right, with sufficiently many iterations, the hope is that, we will still converge to the optimal, but with, more number of steps, right, as indicated by this purple curves. So essentially, for SGD, you may not have the convergence every time, but if you try enough number of times, you should still be able to get the convergence. But the main advantage of SGD, it is, computationally much faster, right? That's why people would prefer SGD. Okay, so so there's some more details, regarding we calculate the gradients, right? And it describes, the iterative algorithm, that how do we update our alpha and beta, the model parameters. I think, yeah, they are quite technical, but the idea is, you see here, we update our alpha and beta, right? Say from step t to step t+1, right? And people have developed a lot of different algorithms trying to, speed up the computation. But yeah, so the key here, right, is that we want to, iteratively solve the model parameters and hope your theta to be converging, right? So so here are some, conditions that required conditions for your gradient descent to be converging, right? In other words, your algorithm could converge to at least a stationary point. But if you're, especially when you're original problem is not like a convex problem, right? If it's not convex, then you may not get the global minimum solution, but a local minimum, right? In those cases, essentially, another thing is you want to try multiple runs of your algorithm, meaning that, you know, like only one fit of your model may not give you the best answer, right? You want to restart the algorithm, try it many times, several times, and see whether whether you know end up with similar model fit result. Right? If your model fit result is stable, that means, you know, your convergence point is likely to be a global minimum, right? Like the good solution that you look for. So yeah, so these are, you know, some Lipschitz continuous conditions on your objective functions, but yeah, they are more theoretical. So regarding the convergence, right, there are potential issues, you know, people call this vanishing or exploding gradients. Essentially, this means your gradient value, right, does not go to zero, right? So, you know, for your algorithm to converge, right, essentially it requires your gradient to, you know, decrease to zero, right? But if you have the gradient that is too large or, you know, too small, your algorithm may not converge, right? So here's just some example of, you know, vanishing or exploding gradients. It's, you know, this would be a more complicated example, right? Essentially, each column here corresponding to one hidden layer, right? So say we have, you know, x1, x2 as our input, but when we have, you know, like too many hidden layers, essentially the algorithm becomes harder to converge. Okay, so so in practice, you know, people would also control this number of hidden layers, right? You do not want to, you know, have too many, so that the convergence may become an issue. Okay. And another, you know, remark regarding the GD gradient descent algorithm is the famous, or, you know, a classic so-called Lecombe initialization, right? So how do you want to, you know, initialize your model weights? And so this may give you faster convergence or less convergence issues, right? So instead of have your initialization exactly to be zero, right? If you choose initial value close to zero, that may be helpful for your, you know, gradient descent algorithm. There's another, you know, paper for further reading if you are more interested. So in real world applications, mostly people would prefer SGD over the classic gradient descent, right? Because of the computational advantage. And essentially, you know, for SGD, at each iteration, you only need to use a subset of your samples, right? So the CPU requirement becomes much lower, or the memory requirement as well, right? So that's a very realistic advantage, for people to use SGD. And there are also, variations of SGD, right? You might encounter in real life, and there's no rule of thumb, which algorithm is the best, but people just have empirical experience, and you might want to try different algorithms to see which one might give you the best solution, right? So so another key concept is the learning rate. We will talk more about learning rate. I think we will see some graphs as well, right? But the idea of learning rate is basically at each iteration, right? Remember when we, for example, update our beta t to be beta t plus 1, right? So the learning rate is essentially the multiplier where how much, right, do you update from beta t. So a larger learning rate means at each step you have a bigger. Yeah, let's see if we have a formula here. Right. So here, essentially this gamma, right? So at each update, whether you have a larger gamma, right, a larger learning rate, means that you would have a bigger update, right, or a bigger step, and a smaller learning rate means at each iteration, your update would be more conservative, right? So so this learning rate is super important when fitting neural network models, because if your learning rate is too large, you are easily miss your stationary point, right? Miss your convergence point. So your algorithm may not converge. But if your learning rate is too small, essentially your algorithm would be too slow, right? That's not desired either. So choosing the learning rate is very important. And then there are some techniques. For example, people do the warm up, right? Or people would decrease the learning rate over time. Different techniques. So so this is so in terms of choosing activation and loss function, it's actually more standard, right? And based on your type of model, whether you do regression model, you would prefer like sigmoid, as it is, like continuous activation function, right? And the mean square error. That's essentially, corresponding to like a linear regression for your link function, right? And then for classification, people use the cross entropy error, which is essentially the logistic link generalized to more than two classes, right? So this is analog to the logistic link function. And people might use, so yeah, as I was saying, right, the most commonly used may be the ReLU or sigmoid activation in both cases. So yeah, here's one illustration of the different learning rate, right? The impact of different learning rates. So as indicated by the different colors, we mentioned if your learning rate is too high, essentially your algorithm may not converge, right? So your loss is not, instead of decreasing, right, your loss actually going up, because every step you update your parameters too much, right? So you would miss the stationary point. So it then do not converge. And then for this low learning rate, essentially it could converge too slow, right? We see that. So here the number of epochs is essentially your number of iterations, right? So this blue curve, we see that it would converge much slower, so that even with a large number of iterations, it may not achieve the optimal point either, right? So another case of high learning rate is also you could converge, right? With a high learning rate, you could converge, but the convergence, it does not, you do not converge to the optimal global minimum point, right? Because with the high learning rate, you essentially, so it's the same idea, right? With the high learning rate, you essentially miss the global minimum, right? You might stuck at a local optimal point. Okay, so at the end, a good learning rate should be something like this, right? It converges reasonably fast, and it should converge to the global minimum point. And on the right panel is essentially how would like a real convergence look like, right? Because, and this is like a typical SGD example, right? As we mentioned, for SGD, each iteration, right, you may not be monotone decreasing, right? So that's why we see the loss is going up and down, right? So essentially your loss is going up and down. But the overall trend, right, is that it would decrease for you to achieve a optimal solution, right? And theoretically, right, if you observe this trend that is too bumpy, right, then you might consider decrease your learning rate, right? So with reduced smaller learning rate, every time you update your objective a little bit, right? So you may be able to get a more smooth, trend, for example, right? So another key thing to clarify is that we know with neural network models, we have a large number of model parameters, right? Especially if we have multiple layers, then your number of parameters would be much larger, right? And we know that the number of parameters corresponding to the complexity of your model, right? So recall that for more complex models, we are more likely to commit overfitting, right? So to avoid this overfitting for neural network models, there are several techniques. Some straightforward idea is essentially we want to control the complexity of model, right? By limiting the number of hidden units or the like the hidden neurons, right? In other words, limit the number of neurons or number of layers, right? Those parameters. Another thing is limit the norm of the weights or penalize the weights. So this is essentially the penalization idea, right? So this penalization idea we have introduced as well. And a more a new idea that is we haven't talked about is so-called early stopping. So the idea of early stopping is that we may not, want our model to be fully trained, right? Instead, we should, stop the training at a desired point where, for example, further updating your model do not improve the performance on validation. So yeah, we will see the example next. But so the idea is that we have seen previously, right? As long as you keep updating your model, the performance or like the training error would be continuously decreasing, right? The training performance is always decreasing. However, we are more interested in the performance on the validation, right? So if the performance, on the validation, so typically, right, with a good model, the performance on the validation would be decreasing, like the loss, right? The loss on the validation would be decreasing at first, but it may, might remain at a certain level after certain limitations, right? So when we monitor the performance on the validation, if the performance is not improving, right, then that means, we should do the early stopping, even if the loss on the training would continuously be decreasing, right? So this training validation idea is, very important in in training machine learning models. Yeah. Yeah, actually, we do not have a plot here, but actually, let me give you an illustration, right? So let's say this is number of epochs, the number of iterations, right, that we train our neural network model. And we have, like we have a blue line, right, indicating the loss on your training samples, okay? So this is the loss. So we know that, as your number of epochs increasing, the training loss is always decreasing, right? However, regarding the validation loss, right, so your validation loss may decrease with your training loss at first, but it will, come to a flat after certain epochs, right? So that's your validation loss. And if we observe, this kind of performance, right, that means we should make the early stop at this point, right? The further training do not improve your performance on validation. And that means, anything beyond that, this is overfitting. Okay. So, yeah. There are some more formulas, but yeah, I don't think. So, we could, write out our model into these formulas, right? I don't think it's very, yeah, so it's not, super important, but essentially if you need to like develop some neural network theories, right, you would rely on those formulas, but that's not the key here, right? So this is just some special cases of neural network. So essentially we can, think of like linear regression as a special case of our neural network, right? Which is basically, you have a single neuron, right? A single neuron Z that connects with all of your input variables. And the matrix spectralization, is another special case of neural networks. It is used for, recommender systems. Okay. So, anyways, so essentially, so far, we introduced this basic feed-forward neural network model, right? And we introduced how to fit the feed-forward neural network, for example, right, with the gradient descent algorithm or the stochastic version, right? We introduced, some key concepts. Let's write them here, right? So we introduce, the layers, right? What we mean by hidden layer, input layer, output layer, activation functions, right? The meaning of activation, and also the link function, right? To link with, for continuous or categorical outcomes, you should apply different link functions, right? So through the SGD algorithm, right, we talk about, the learning rate, how the learning rate would affect your model fit, right? And the batch size, right? So essentially, the batch size is the number of samples that you use for each SGD iteration, right? So the batch size together with, the number of epochs, right, that controls the convergence of your neural network model, right? So these are, all the key concepts that we have introduced. Hopefully, we all get a good sense of their meaning and how we could, actually utilize them in real problems, right? So now we move on to so-called deep neural network, right? So I'm sure, you have heard about like the word of deep learning a lot, right? Deep learning may be, even more sounds fancier, right? Even than machine learning itself. So, but the point of deep learning is essentially you have more and more complicated models that you assume, right? So deep neural network, right, is a typical, example of deep learning models, right? And it refers to, neural network models with many layers, right? A large number of hidden layers. And typically, for some deep neural network examples, so just, some examples, right? People develop like VGG or, ResNet or, ImageNet, so on and so forth, right? All of these different network models, they might have, dozens or even over 100, number of layers, right? So the number of layers could be much larger, right? So that's what we mean by deep neural networks. So, so the fundamental idea of neural network has been, around for a long time, but it becomes more and more popular essentially because of, the computational power that we are able to fit these models more efficiently, right? So for this super large, models, your number of parameters would be, in the order of millions, right? So, these alpha and beta values, easily you could get, over 1 million alpha and beta parameters that you need to fit. So without the computational tools, they are not feasible, in the 20th century, for example, right? But in the 21st century, with the development of the computers, we are able to fit these more complicated models. So here's one illustration, right, or the example of deep neural networks. So for example, people want to learn this hierarchical feature representation, right, of people's faces, right? In other words, this is a feature extraction problem, right? You want to extract features, from all the faces, and with the extraction, right? People even could do, people could do the face recognition, right? Recognition, or actually generation, right? You might have heard, those like AI generated faces, right? Or AI generated celebrities. They are all based on this, feature extraction as the first step, right? And then you can do further, additional works. So the idea is that with multiple hidden layers, right? Essentially, we want to extract those features at different levels, right? For example, this hidden layer 1, you actually extract the features at a very abstract level, right? You couldn't really tell, for the hidden layer 1 presentation, like you might only tell, like which part of the face they are from, right? But it's hard for you to describe these neurons, right? But for hidden layer number 2, they become more realistic, right? Maybe some features corresponding to the shape of the nose, shape of your eye, your eyebrows, etc., right? So hidden layer 2 is they are more realistic. And then with the hidden layer 3, it could it give you something like the shape of your face, right? Or the shape of your forehead, something at a higher level, right? So this is the potential potential advantage, right, of using multiple hidden layers. Essentially, you could extract the features at different levels, right? And so like what you output, right? It could be some classification, right? For example, you want to classify as male versus female, or young versus old, something like that, right? Or you can directly output the features, right? The features as as I was saying, your forehead, your nose, your eyes, etc., right? And then with these output features, you can even further append another neural network to the extracted features for face generation, right? You want to generate new faces using these extracted features, right? That's something else we will briefly talk about later as well. So this kind of deep neural networks, a typical example is the so-called convolutional neural networks. and they are most important when applied to image data. Okay, and we will see why the convolutional neural networks, they are suitable for image data. So CNN, it is based on the idea of convolutional layers, right? So so the idea of convolutional layers is that we want to build the neurons that's based on the local region, okay, the local region of your input space. Biologically, the neurons only take signals from neighboring neurons. It's similar as like the K nearest neighbor idea, right? So for each neuron, we only want to take information from a certain neighborhood that we define. So that's the idea behind the convolutional layers. And we will, yeah, this is just never mind. Some illustration of how the hierarchical structure actually is represented in human brain, right? But yeah, anyways, we will focus on the convolutional layers. Okay. So here's one example. So as I was saying, right, the CNN is mostly applied to image data, right? So think of this input layer is essentially like a 40 by 40 images, image, right, that we input. And here the 40 denotes the number of pixels, right? You could think of this as number of pixels for your image. And so we call like this one convolutional layer, right? We call this one here one convolutional layer is essentially each one of the neuron here, right? That's like one neuron in the convolutional layer. It takes the information from this 5 by 5 neighborhood, right, on your original input. And so we call this 5 by 5 neighborhood as the so-called filter, right? You can think of, like the filter of your camera, right? So this one 5 by 5 filter, we can move, right? We can move this 5 by 5 filter, throughout our whole input image, right? Like move this filter throughout the image so that we get a reduced or, like a more concentrated convolutional layer. So that's why, this dimension for the convolutional layer, we see it is smaller than the original 40 by 40, right? And we actually, allow overlap, right, of the filter, as the filter going through the whole input. So the dimension of the convolutional layer may be something like, 30, like 36 by 36, for example, right? But it is, reduced than the original input, right? And we could apply these convolutional layers like multiple times, right? And for this filter, it can be 4 by 4 or, other size, right? Every time you apply the convolutional layers, your information is more and more concentrated, right? So that's why the dimension, of the convolutional layer would decrease right here. And, after several convolutional layers, if we think the information, like the extraction is well enough, right? Oftentimes we would use the so-called flatten, meaning that, So this is something like three-dimensional, we can denote this as like d by q, right? So after several convolutional layers, this is three-dimensional. But we want to, flatten it into, for example, a vector or a matrix, right? And then we apply some fully connected layers. And this is actually, basically, we go back to the feed-forward neural network that we have learned, right? So the fully connected layers, they are essentially, the feed-forward neural network, where all the neurons are connected to the next layer, as we have seen, right? With the fully connected layer, we basically do the linear combination and, use the activation function, right, to model our features that we have selected or we have extracted. And the last step is to use the link function G, to connect with our output layer. So this is, like a illustration of how the CNN structure, right, looks like. Let's see if we have this example. Yeah, I believe this is just another. Anyways, yeah, it looks like the example is out of date. But what about this one? Yeah, let's see. Oh, okay. So this is showing, during auto drive, right, how the image. So you can think of this as image segmentation, right? You want the, on the right hand side, right? You want your machine to be able to, recognize different subjects, and the fundamental idea is exactly through those convolutional layers that you are able to extract the features, right, from either images or the videos, right, the continuous feed of images. It's just one illustration. But yeah, so this is more of like an abstract showing, right, of the CNN structure or architecture. But next, we will try to get more detailed understanding. Okay. So this is another similar illustration as the previous one, right? But as we see previously, for example, this is maybe your 5x5 or 3x3 filter, right? And after the filtering, you get a single neuron in your convolutional layer. And the point here is you could have multiple filters, right? So these 3 feature maps, meaning that you could have 3 different filters that essentially try to give you different information, right? And later we will see the exact examples of how the filters look like. And so the more and more we do the convolutional layers, essentially we would reduce the dimension of our image, right? But increase the number of maps, as we see here, right? The number of maps is increased. And once again, right, at the end, we want the fully connected network, which is essentially the feed-forward neural network we have learned, right, for this later part. Okay, so so here's the more detailed example. of what we mean exactly by filters. Okay. So on the left-hand side, this is our input image, right? So the input image, for simplicity, right? We can think of this as a black and white image. So you just have, 0 and 1 as your pixel points, right? As your pixel points. So this is your input. And for a 3x3 filter, right? we need to, define the filter. For example, this filter is, extracting the diagonal information, right, from your raw image. As we see, the diagonal entries, they are 1, right? And then the off-diagonal entries are 0. So that means when we apply the filter, to the raw image, it extracts the diagonal information of your raw image. And how exactly, right, we apply the filter? It's basically, we overlay, right? We overlay this filter to, the first local region by this blue square, right? So this blue local region where we overlay our filter, and the convolution, right, is defined as, simply you take the summation of the multiplication here, right? So here's the summation of the multiplication, meaning that you do the entry-wise multiplication, right? Entry-wise meaning, the 1 entry, right, is 1 times 1. Then the second entry-wise multiplication is 1 times 0, and then 1 times 1, and 0 times 0, so on and so forth, right? And then you take the summation, right, of this, entry-wise multiplication, and that is called the convolution, right? So because, this is diagonal entries, right, essentially we are counting the, so essentially we are taking the summation of the, ones on your diagonals, right? That is why we get the 4, after, or that is why we get the 4 on our feature map, right? In other words, on our convolutional layer. And, so this intercept, right, is optional, right? Sometimes you just take the intercept of 0. But so this is what we mean by, apply the filter to the input image, right? And then as we move this filter along our input image, right, we get the different convolutions, right? So here, we move the filter to the right, right? Then we get this region, right? We do the convolution where, the or the diagonal entries, there are 3 ones, right? That is why, we have 3 on the feature map, right? So, so as we, as the filter, goes through the whole input image, right, we are able to get the values of our feature map. And we see, the feature map is with reduced dimension, right? The key here is, we could define the multiple filters, right? So this 3x3 filter, is not unique, right? This 3x3 filter is, like extract the diagonal information, right? But for example, we could, define a filter with only, like 1 in the center, right? And then all 0 otherwise, right? This is also another filter. Or, we could have a filter that is, taking once on the boundary, right? Or the outside of it, right? Or something like, yeah. So the point is, you can define all sorts of different filters, right? And then you apply the different filters to your input image, do the calculate the convolution, and then you end up with your feature map, right? So that's the idea. And by the way, this stride size means, the stride size, like how much does your filter move, right? Stride size equal to 1, is stride size equal to 1 is this example, right? Every time we move one step to the left or to the right. Stride size equal to 2, meaning, every time you move two steps. And then this multiple filters, right? People call this the depths. So, this corresponds to this number of feature maps, right? As we see here, you apply 3 filters, right? You get 3 different feature maps, and so on and so forth. Right? So, so here's another example, right? So in addition to the convolutional layer, right? So this is like essentially a convolutional layer that we apply. We also want to further like reduce the dimension, right, by using this so-called pooling layer. So as we can tell from the name, right, pooling means we want to pool the information at each local region, right? So here is an example of max pooling with 2x2 filter. So each region, right, is a 2x2 local region, and by max pooling meaning we only take the maximum entry, right, at each local region. So this 6 corresponding to the 6 after max pooling, right? And for the next 2x2 region, the max pooling gives us 8, and this max pooling gives us 3 and 4, right? So clearly we see that using max pooling, we reduce the dimension from 4x4 to 2x2, right? So max pooling is essentially for dimension reduction. Essentially also control your model complexity, right? So there are you could use max pooling or mean or medium pooling, etc., right? These are 3 most commonly used pooling filters. And so using the pooling, right, do not change the depths, right? So you remain the same depths after you do the pooling. For example here, right? So from here to here, right, we see that from the convolutional layer we have 3 feature maps, and after pooling, we still remain to be 3 feature maps, but we see the dimension is reduced, right? That's the the goal of pooling layer. Okay, so that's pooling layer. So yeah, let's take a break here. Hopefully we get a sense of how the convolutional neural network is defined, right? And then later we will continue. Yeah, let's come back at 12:40. I want to say.
So I have a question. Why not 2 instead of 3?
Why not you mean like the filter size?
Yeah, max pooling, like you pull this 6, then 8, then 3, then 4, but it should not be 2, 4.
So max pooling meaning that you extract the maximum value within the region, right? So the maximum value, within each region, here it is 3, right?
Oh, thank you. I got it.
And so if you apply like a mean, right? If you apply a mean pooling, that means for each local region you would calculate the mean and put it to the right, right? Yeah, but max pooling is like one of the commonly used ones. Yeah.
Thank you.
Okay, so there are some questions in the chat area. I don't know if you want to address them before the break.
Let me see. Yeah, sorry, I didn't open my chat. So is there an optimal number of hidden layers? That really depends on your problem, right? The data you have. So I want to say, typically with like a problem that is not too complicated, you want to start with 2 or 3 hidden layers. That's a good starting point. Unless, right, you are doing deep neural networks, and nowadays people really if you want to do deep neural networks, you oftentimes right you need to have like a massive data set, right? You should at least have thousands or tens of thousands samples for you to fit deep neural networks. And for more smaller scale problems, yeah, I think starting with like 2 or 3 hidden layers is a good choice. And piecewise convergence. Sorry, so so what do you mean by piecewise convergence? I believe this is, so the convergence we define here is based on the objective function, right? We define our like loss function. For example, the loss function, like we use R, right? Piecewise convergence. Yeah, I'm not sure if piecewise convergence, I do not know the exact meaning. Maybe, yeah. For the evaluation. The link for the evaluation. Yeah, so standard to move from left to right. Yeah, so I think to your last question, yeah, that it's the point of moving your filter, as long as you go through the whole input image, right? And that is fine. And but move it from left to right or from top to bottom, it doesn't really matter, because you see that your the location, right? The location of your convolutional layer, it is one-to-one match, right, between your original input layer and the feature map, right? So for example, the top leftmost, right, would be matched to the topmost corner in your feature map as well, right? So the direction that you move your filter doesn't matter, because there is a one-to-one correspondence. Yeah. So yeah, I guess I'll converge in small groups. Oh, so small groups, you mean like subset of your samples, right? I guess, I suppose, you mean like subset of your samples. Yeah, that's an interesting question. I think because for example, when we use SGD, right? Although at each iteration we use a subset of samples, we evaluate the because throughout the iterations we will use different subset of the samples, right? So essentially, all the samples will be used after certain iterations. So I want to say the convergence is still evaluated using all the samples. So so basically, yeah, the convergence is defined using all the samples. So I mean, like we do, like if it only converge with like subset, that's not good enough, right? We want the convergence of all the samples. Yes. So yeah, I we can continue with other questions after the break. Okay. Yeah, I need to get some water. I'll be back. Questions if you have any. So I see, yeah, William, you have, yeah, I do not know what you mean. Oh, satellite navigation.
Yeah. So when you were showing the autonomous vehicle with the obstacle avoidance, so the question I had was, is it solely object avoidance, or is it using some form of additional intelligence such as satellite imaging?
Oh, I know what you are saying. So right. So I want to say, so basically the detection of the different subjects, right? That is simply an image segmentation problem. That you do not need, the navigation part of it. It's basically you have the input, your camera input, right? And it is live, right? So your camera input of, the continuous images, and then you run your convolutional neural network, right? More, definitely more complicated than just a few convolutional layers, but it's essentially a deep neural network model for you to, detect these different subjects, right? And yeah, I don't think it's, related to navigation, but yeah, autopilot part, right? Definitely, you need the navigation for your route calculation, etc. Right.
So that also brings in the idea. So I think what's the name? The Tesla guy. He was more towards. He said instead of radar, he likes LiDAR, right? LIDAR. Is it because of that, right? Is it doing? I mean, is it the reason why he's more into LiDAR instead of radar?
So RIDAR. Oh, I see.
Yeah, LiDAR. Yeah. So that's more vision, because that's able to tell colors instead of just, hey, there's an obstacle or there's an object.
Right.
You say radar says there's an object. It doesn't say white, blue, green, or red. But LiDAR says red, green, blue. Because as you were going, I could also see that there were some instead of just seeing object, you see that it's able to also detect the color of the object.
Yeah, I know. I believe one thing Tesla did, with like unintended, objects, right? Or on anything that's out of normal. Essentially, it has some like trigger some emergency system, right? For example, emergency brake, right? I think that's one thing, Tesla was doing. But essentially, from the neural network perspective, it's like you want to train your model, right? Train your algorithm for it to be able to detect, those abnormal objects, right? So for example, like another car, right? It has some, illegal merging, right, into your lane. Those kind of situations, you want the algorithm to be able to, detect those illegal merging, and then maybe after that, apply the emergency brake, right? Yeah, I think that's from the model perspective. So you want to basically specify the like the object, right, that you want to detect. Okay, so I think another question from MS. Yeah, 1 second. Yeah, I see a raised hand, but so a previous question from MSA. Is there a link for the evaluation? I'm not sure. Yeah, what do you mean by link for the evaluation? Maybe, yeah, you could type in the chat.
Yeah, I think it will be, so anything you need that you don't have, please put it in the chat or put it in Slack, and then someone will. So anything of evaluation, attendance, and things like that, just put it in the Slack. Yeah.
And so do we have a question from Azad? Yeah.
Yeah, I have a question. Like you showed the 5x5 tree image to 3x3. So how to get the diagonal value, but it's not overlapping? So like first it's a 5x5, then 3x3 diagonal 1, 1, 1. Then the over, how to get it that one? It's not overlapping.
Yeah. So what do you mean like not over? So are you saying because like we apply the 3x3 filter sequentially, right? We would so like this red circle here is the first first entry, right, that we apply, and then we move it to the next location, right, and then we move it to the next location. So they would corresponding to the second and third entry here, right? Does that answer your question, or you mean something else?
One bias 0, that one filter 3x3. Okay, so that one. Okay, thank you.
Did that answer your question?
Yeah, because that's why in the middle 3x3 there was a confused. Yeah, okay, I got it. Thank you. So it's overlapping.
Right. Yes.
Kind of.
Yeah. So yeah, it is overlapping. Yeah. So you allow the filter, to overlap, and that is controlled by the stride size, right? So we call this the stride size. So if your stride size equal to 2, that means you move like 2 steps at each time. Yes.
Thank you.
So another question: specific filters are typically used, right? So actually, when we run those CNN models, in most cases, actually, you know, like in your Python implementation, right? The filters, they are predetermined. You know, there is like a, you know, list of commonly used filters. You do not need to like choose like which filters to apply, but so what you choose is the filter size and number of filters you want to apply. So for example, whether you want to choose like 3x3 filter or, you know, 5x5 filters, right? And the number of filters, you know, at the end, you know, whether you want 3 feature maps or, you know, 10 feature maps, right? But so actually all the filters, they are quite simple, right? Because, you know, you want the filters to, you know, like extract the information, right? So diagonal filters or, you know, off diagonal filters, those those are like the typical filters that people, you know, you just apply those commonly used filters. You do not need to worry about, you know, like creating new filters or, yeah, like picking the filters.
But how do you know that which is the best?
So the best is not, you know, like in terms of which filter you choose, but you know, the filter size and number of filters. So it is more important. So it is I think the most important is like, you know, whether you choose 3 filters or 5 filters, and also the number of convolutional layers you want. So those are the more important model specification. Yeah, if that makes sense. So typically, yeah, you do not need to like worry about, you know, like specific filters. Yeah. Yeah, so I think, yeah, we could, you know, look at some examples later. Any other questions, you know, regarding convolutional neural networks, maybe first? Yeah, so I think the key here, right, is basically we introduced the architecture like this, right, the convolutional layers, the pooling layers. And then, yeah, so any questions, you know, regarding the previous topic? Yeah, we talked about the feed forward neural network, right? So
I have one question. So is the convolutional layer and pooling layer usually alternate? Because in this
yes,
example, you have convolution and pooling.
yeah.
So what is the main? I think you talk about the main reason to do the pooling is the dimension reduction. But if you keep doing convolution, like say using different size of the filter, so I think you can also reduce the dimension that way. But what's the specific reason to do that pooling after the convolution?
Right. Yeah, that's a very good question, you know. So yes, you know, we do pair convolution and pooling in most in most cases. And so essentially, you know, you have one convolutional layer, one pooling layer, they are together, right? And so actually the convolution layer do not, you know, reduce the dimension significantly. The good example, I think, is here, right? You see the original input is, you know, like 40 by 40, right? And you apply like a 5 by 5 filter, it's actually a pretty large filter, right? So typically, you know, people use like 3 by 3 filter, right? So with a 5 by 5 or 3 by 3 filter, you know, you only reduce the dimension to, you know, 36 by 36, right? After you apply the filter, it's not reduced very much. However, you know, if you if you simply do like a 2x2 pooling layer, right, then the dimension is essentially reduced by 4 times, right? You would reduce, 36 by 36 to 18 by 18, right? That's, like a more significant dimension reduction. And if you do, actually like a 3x3 pooling layer, then it's even more, right? So you would, reduce your dimension to 12 by 12. So convolutional layer itself do not actually reduce the dimension very much. So yeah, that's why, actually the pooling layer is more effective in reducing the dimension. And actually, right, otherwise, without the pooling layer, if you have multiple filters, right? So if you do 3 filters, actually after convolution, you get 36 by 36 by 3, right? Meaning the 3 filters. You actually increase your dimension, without the pooling. So, yeah, yeah, did that answer your question?
Yeah, thank you. But looks like if you if you choose a relatively large dimension of filter and use a large stride, a relatively large stride in convolution, you can still reduce the dimension relatively large.
Right. Yeah. That's some good thinking. So a potential issue is, people do not prefer a larger filter. Is basically, and also people do not prefer larger stride size. That's kind of you actually lose your information, right? So apply like a large filter with, like with large stride size. It's kind of like you blur your image, right? You essentially, make your image like really reduce the quality of your image after the convolution. So you might, lose like valuable information, or you couldn't, detect like the features. Maybe you couldn't, you might like lose the important features. So people try to, keep the filters to be small, and, your stride is typically, 1 or 2, like that. Yeah.
Thank you. But looks like if you use the maximum pooling, you still lose information, right? But what you're saying is that may rather lose less information than you use a large stride, right?
Right. So for example, we think of, like max pooling, right? I wouldn't say it's like lose information, but you actually, so you already extracted the information from the convolutional layer, right? So what max pooling does is essentially, they want to emphasize on the more important features, right? By max pooling, you only keep the, the largest value, right? With max pooling, you keep the largest value at each of your local regions. So that's basically, you can think of as feature selection, or you keep the most important feature, right? So I think, yeah, that's what people find, more useful.
Thank you.
Yeah, very good questions. I think they are, good thinking, in order to better understand the convolutional neural networks, right? Okay, so one more question. Pooling or convolutional alter the precision? Yeah, so I guess, so my interpretation of your precision is basically, right, so for example, at the end, we want to do some classification, right? And the precision, can be measured as, the accuracy of doing classification, right? So I want to say, you know, most relevant to the precision is essentially, you know, like the architecture, right? So by architecture, we mean, you know, like the structure of your CNN model. And there's no, so there's no like rule of thumb, you know, what kind of structure would always be the best, right? Depending on your specific question, a very important, you know, step in fitting deep neural networks is the model tuning, right? So by model tuning, it's actually, you know, tuning a lot of things. You know, take this CNN for example, right? We want to we want to tune, you know, regarding your filters, right? Your filter size, number of filters, etc., right? And we want to tune, you know, the number of layers, right? Whether it's, you know, the number of convolutional layers, or even the structure of your fully connected model part, right? And in addition, you know, the previous ones we have already seen, you know, like the learning rates, right? And together with learning rates, you know, the number of epochs, right? That's essentially related to, you know, early stopping, right? And also, you know, the optimization algorithm, right? So we call this, you know, whether SGD or, you know, other algorithms like ADAM or adaptive, you know, some algorithm, right? This is called the optimizer. That's another thing, you know, people tune, right? So at the end, you know, the performance of your model, right? The precision of the result is determined by the combination of all these model tuning. So, so that is why also, you know, why people call this the black box, right? It is because we have so many different factors that, you know, affect your final precision or your final result. It's hard to, you know, like pinpoint, you know, like which component is most important, or like how exactly, you know, each component plays their role, right, in terms of the overall model. But it is more like, you know, empirical experience that you try to tune all these aspects of your model and try to get, you know, like a better model performance. And it sometimes, you know, it lacks the interpretability, right, of your model. Did that answer your question? So the pooling or convolution, you know, like the filter and the pooling themselves, you can think of them as like the basic units of your model, right? So you know, it's so this is like saying, you know, you build a house with bricks, right? The bricks themselves, you know, there's, you know, little variation to the bricks, but it's more like the overall design of the building, right? And then, you know, the decorations or, you know, like the structure that you put onto your building that affect the final product, right? And the bricks themselves, you know, they are just the building blocks, right? Yeah, hope that's, you know, a good analog to your question. Okay, so so yeah, let's move on, you know, to see some additional materials. So yeah, there's some computational, concerns, and I think one key point is actually we want to keep in mind that for CNN models, the number of parameters is actually much smaller than, like a fully connected feed-forward model, because essentially, you given like a filter, right? You only, apply the filter to your whole input image. So number of parameters is dependent on the filter, but not dependent on the input, right? And so so actually CNN would have like a much smaller number of parameters. That's the point here. Yeah, anyways, so in terms of number of parameters, the fully connected part, right? Fully connected part always, contributes to the most number of parameters. Okay. Okay, so one more example, it's actually also build upon CNN, right? So from CNN, people could take a step forward and define the so-called autoencoder, right? So autoencoder is a type of neural network models, and the goal of autoencoder is essentially, so it has, these like two parts, right? The encoder part and the decoder part. So we think of, you can think of the encoder part as a CNN model, right? For example, you apply your convolutional layers and you get your features, right? Essentially, after the encoder step, you extract, some features, or we call them the codes, right? From your input, right? And then, using these extracted features or the codes, right? The codes that you generate, you apply, the so-called decoder that is on the opposite direction, right? Opposite direction that you generate, right? Generate the output that is, actually the same format as your input values, right? So for example, your input is an image and your output is also an image of the same size, right? But it is based on the features. Oh, sorry. It's based on the features that you generate, the features that you extract, right? And then you generate the output. And sometimes people also call this the latent space, right? Meaning that this latent space is not directly observed, right? But it is derived from your encoder part of the model. So for example, right, people could use autoencoder to for like image enhancement, right? So enhance right your image. Some other applications may be, as you could generate similar images, right, as your input. So for example, you train your autoencoder, right, with a large number of paintings, right? So you give like famous oil paintings, like tens of thousands of oil paintings, right, into your autoencoder model, and then you want the model to learn the features from the paintings, right? So that it could generate, AI paintings, right? That's mimic the historical you know, the famous ones. That's basically the idea of autoencoder. And so it has two steps, right? You know, the first step is to learn this lower dimensional representation, or, you know, lower dimensional feature extraction, right? And then, you know, capture the most important part, right, of the input. And then for the decoder part, you know, it can be used for different applications that, you know, we are interested in, whether, you know, facial recognition, feature detection, anomaly detection, right? Anomaly detection meaning that, you know, you might have, you know, additional input, right? Or like the future input that you that you feed to your machine, and you want the machine to tell you, you know, whether this future input has anything abnormal, right, from the previous images. For speech recognition, yeah, actually, I haven't done this, you know, myself. I'm not exactly sure, like how the autoencoder, you know, is applied. But anyways, yeah. So this, so here's another example. So this is, you know, actually similar to the autoencoder idea, right? For the specific, you know, this is called the UNet, and so the difference is that for image segmentation, right, you want to output the segmentation. You can think of this as an overlay, right, onto your original input image. You know, like different segmentation parts, right, of the input image. But the idea is the same in the sense that, you know, you have the, you know, encoder part, right, where you do feature extraction. You know, you get the important features, and then these are the, you know, latent features, right, that you find. Then in the second, you know, decoder part, basically based on the features, right, you want to identify the, you know, different parts of your image, or different objects, right, that you could identify from the image. Let's take a look at, you know, this example is, I think we see this at the very beginning, right? I think now we should have a, you know, better understanding of this application. Essentially, we have the optic disc image, and the segmentation, right, is an overlay. You know, this overlay of the, in this case, right, it's the rim versus disc, right? So we call this, you know, so we call this narrow area in between, right, the rim that we try to, you know, segment from the raw image. It's just one example, right? Yeah, I do want to, you know, give you some Python applications. So let me try to find some examples. Okay, yeah, I do have some examples. Let me see. here. Okay, yeah, let me share my computer. 1 second. Okay, let me open the application. So so there is some, you know, prerequisites, you know, for you to run Python, right? But yeah, so for example, you know, I think a good, like for beginners, I would recommend this so-called Jupyter notebook. That is, you know, one Python application, right? So it is, you know, more interactive for you to, you know, code Python, and you should be able to, you know, find tutorials, right? How to install your Jupyter notebook, and essentially after install Jupyter notebook, you know, you are able to run the Python program, and yeah, actually you can even, you know, run R, you know, on in Jupyter notebook. It's just, yeah, it's just like a coding environment, right? So then there are, you know, a lot of examples online. Yeah, I think it would be, you know, easy for you to find Python examples for neural networks. But yeah, let's take a look at this example, you know, and this, you know, you can easily Google search this one as well. So intuitive deep learning, right? For example, if you just Google search this, there should be a so there's like a post and also a GitHub link, I believe. Yeah, so I can, you know, put this in chat and for your future reference. Yeah, there should be a Python link. Sorry, GitHub link. Let me see. This is, you know, it just gives you some fundamental definition, but where? For example, this one, I guess. Yeah, this is, you know, like a neural network example. This is a CNN example, right? Wait, yeah, anyways, so, you know, you should be able to find the GitHub link as well. But, you know, since I already have this one here, right, we can try to go through this together. So the first example is, you know, how we could build a neural network in Python, right? So similar as, you know, R libraries, you know, Python also has, you know, its own libraries. And for example, pandas, right? It's a data manipulation library, and Keras and TensorFlow, you know, we will use them later as well. So we import, you know, our library that we need to use, and it's house price data, right? It is, you know, you could download it. You could download the data from, you know, the website. Then, you know, we load the data, right? We can print out our data. So it has, you know, several variables, quite, you know, standard data structure, right? And so we can convert this data set into, you know, matrix, right? We do not want the data frame structure, but, you know, we only want to keep the numeric values. So for example, this is a corresponding matrix, and we split data, you know, into the input features and labels, right? So, in Python, the index starting from 0, right? So your X is, basically the first 10 columns, right? And your last column is the outcome, right? Above median price. So this is a binary outcome of interest. Y, right? That's saved in Y. You can, print the dimension, right, by the shape function, right? So the shape of your data is the dimension. And some additional, Python library. And typically, to fit neural network models, we want to scale our variables, right? So the min-max scalar is simply, you change or you normalize all the variables, right, into, between 0 and 1, right? That's the X scale, right? After the scaling, you see all the input is, between 0 and 1. And we know, a very important step, right, for training your neural network model is to, do the training testing split, right? So here we do our training test split, and we can, specify our test size to be, so, so here is actually, we have, 70% as training, and then 15% each as your validation and testing, right? So this is, over 1,000 samples as the training sample, and then 200 each for the validation and testing sample size. Now we, start building our neural networks, and in Python, I think a more beginner-friendly, right, library is the Keras library. It has, most of the implementations. Wait, I guess let's and let me add something here. Let me check. I think we want to, import TensorFlow first, and then so one update is, I think wait, it should work. TF. Oh, let me okay, so this works. And so one thing is actually, Keras and TensorFlow used to be like separate libraries, but in recent years, they basically, they combine together. It's actually, easier for user to use, right? Essentially, you import your Keras directly from TensorFlow, and yeah, it's easier to use, basically. So within Keras, there are different neural network models, as well as different layers that people could use. So so this sequential model, right, is essentially, the feed-forward neural network that we have seen. So by, this is where we specify our model, right? We have 2 hidden layers. So the dense layer, meaning, it's fully connected, right? So that's the basic model that we have learned. Activation function, right? The ReLU activation. And in this case, we specify our input shape, to be 10, right? We have, 10 features. And the second dense layer, you know, also 32 neurons, right? So not 30, right? But you know, we in this example, we specify 32 neurons, right? But that's, you know, something you can change as well, right? You could, you know, use only 16 or like even smaller number of neurons. You can tune, right? So this is like a very, you know, simple new network model that we specify, right? After specify this, you know, model, I think, yeah, we can also call like model dot summary. Is the right one? Wait. Yeah. So model dot summary, right? You see that this is, you know, your model structure, starting from, you know, like first hidden layer, second hidden layer, and then your output layer. And this also gives you the number of parameters, right, actually in your model. So in total, you know, even with this simple model, right, you have close to 900 model parameters. Okay, so after specifying the model, we need to specify, you know, what optimizer, what loss, right, what evaluation metrics we use, you know, to fit the model. So SGD, right, we have learned this stochastic gradient descent. And another, you know, commonly used optimizer is the so-called Adam optimizer. Yeah, I think these two are most commonly used. And then for binary outcome, right, people mostly use, you know, the binary cross entropy loss function. This essentially defines the objective function, right? And the metrics, you know, because you know, it's a classification problem, right? So accuracy meaning, you know, you want to evaluate the accuracy of the prediction or accuracy of the classification. But for continuous outcome, right? For example, you can use MSE as your metric, right? So on and so forth. So with, you know, model compile, and then we could, you know, run our model fit, right? So when we run the model fit, we need to specify, you know, this batch size at each iteration, right? How many samples do you use? Number of epochs, right? So, you know, how many, so that means you would go through your full data set, right? You would go through your training data set 100 times. Right? In other words, you know, you will use each each observation of your, you know, training sample 100 times. And here verbose equals false, meaning, you know, you do not output the steps, but, you know, we can look at the training steps. So verbose equals to true. And you can also, you know, specify the, so you fit your model, right, on the training set, but you evaluate your model on the validation set, right? This is when we, you know, fit the model. And as you can see, right, so the, you know, actually how the model is run is, you know, it's fitted for each epoch, right? Each epoch meaning, you know, each run of your data. And then it gives you, you know, it could monitor like the loss, right? So you want to see your loss that is decreasing, right? As you see here, you know, as your epoch, number of epoch increases, right? Your loss should be decreasing, your accuracy should be increasing, right? And then you also have the validation loss and the validation accuracy, right? So that's, you know, something you could monitor with your model training. And another thing is that you want your training and validation loss to be close, right? If your training loss is, you know, keeps decreasing, but your validation loss kind of stop decreasing, that means overfitting, right? As we have mentioned. And you know, you want your training accuracy and validation accuracy to be close as well, right? So all the way, you know, because we specify our epoch to be 100, right? So after 100 epochs, we see this stops, right? And we also see, you know, kind of your loss does not change anymore, right? So that means your algorithm convergence, you get, you know, an accuracy that is close to 0.9, that is pretty high. So I see a question, what happens if you scale after splitting? Yeah, so so basically we should not do it, right? You know, we want to scale our variables before splitting so that it is, you know, uniform, right? Yeah, I think you should do the scaling before data splitting. Yes. And we are not using stochastic. No. Yeah, we are using, right? So the model compile here is, you know, we specify stochastic gradient descent. And so, yeah, maybe, you know, you might have noticed, right? When the algorithm runs, it shows like an arrow, you know, that's like a moving arrow right here. So that means, you know, for the stochastic gradient descent, each iteration is, you know, this batch size, right? You fit 32 samples. That's, you know, corresponding to the batch size of your stochastic gradient descent algorithm. So that's each iteration. And then like with this, you know, this is not exact, right? But the idea is with like a certain number of iterations, you go through the whole training data set, right? One time. So that's the epoch, you know, one epoch means, right? One time, you know, you go through all of your training samples.
Yeah. So the 32, what 32 means that sampling, we basically splitting for one epoch, we running it 32 times, and so the update.
No.
So
no, not 32 times. So the batch
I mean,
size.
32 samples.
Yeah, 32 samples, and actually, you know, essentially your number of iteration for one epoch is basically your training sample size divided by your batch size, right?
Okay.
That's the, you know, number of iterations.
Okay. So then that update, which says, oh, I see. So that update is done. Those double equal to with the update is done on each of the 1/32, 2/32, and we are seeing the 32/32. We are not. Yeah. Okay. That makes sense.
Yeah.
Okay. Cool.
So yeah. So actually, for each iteration, right, you update your loss and accuracy, but you know, you only print out, you know, for each epoch, right? Otherwise, it's, you know, too many output, right? You just you know, output for each epoch, like what's your current loss and accuracy. Yeah. Okay. So this is the model training part, right? We see that for this example, you know, it kind of shows convergence, right? And so, you know, then we use the evaluate function, right? Model evaluate on our test sample. So if we run this, we see that, you know, it gives like a test accuracy, right, of 0.86, which is, you know, reasonably well, right? So next, you know, we want to show some visualization, help us, you know, understand the process, right? So this is the library matplotlib, right? This library, you know, gives you some plotting options. Then, so this plot is basically we want to plot the loss versus the number of epochs, right? So we see here, you know, the training loss, right, keeps decreasing. The validation loss, you know, is close to the training loss, which is good, right? Meaning there's no overfitting. And, you know, potentially you could increase your number of epochs, right? Maybe to 200, and you could, you know, get even better or, you know, more conversions, right? But another thing is, you know, we look at the accuracy, right? So in terms of the accuracy, training accuracy, you know, keeps increasing. Validation accuracy is a little bit more wiggly, right? Because it is, you know, separate from your training data, right? And the good thing is, you know, there's no indication of overfitting, right? In this example, they are pretty close to each other. And so yeah, that's pretty much, you know, we fit like a simple neural network model. So next is, you know, more like for illustration purpose, right? So this is a quite simple data set, you know, and we want to show the application of regularization, right? So this is something we have learned, you know, whether you add penalization, right, or regularization to your model, you can do the same thing with neural network models as well. So to illustrate this, you know, basically we first start with like a complicated model, right? Essentially overfits our data. So this second model, you know, we specify like 1,000 neurons for each of the hidden layer, right? And we specify 4 hidden layers. So this is essentially like a overfit model, right? So let's run this model, you know, because the model is larger, right, bigger, so it takes longer time to run. But yeah, it should be in a couple of minutes. But yeah, so this is like the plot from the previous previous run I have done, right? It should be similar. Yeah, okay, we are done with this one. So let's see. Yeah, you get a similar pattern, right? So this is a typical overfitting, right? Because, you know, your training loss keeps decreasing, right? But your validation loss actually goes up. So that means your model gets too complicated, you know, it's not a good fit, right? Indication of overfitting. And same thing with your accuracy, right? Maybe, you know, your training accuracy is always going up, right? But your validation accuracy do not improve anymore. So to address this overfitting, right, there are, you know, different ways actually. So so one way is, you know, the kernel regularizer, right? So that's essentially, you know, the penalty term that we could add to each layer, right? So you can specify, you know, L1 or L2 penalties, right? With, you know, like the different tuning parameter. And actually more, I think what people use more is this so-called dropout layer, right? So this is called dropout layer, meaning that, you know, you would randomly drop out a proportion of the neurons that you have from previous layer. So this means, you know, in the previous layer you have 1,000 neurons, right? Then you randomly drop out 30% of those, you know, 1,000 neurons. So that's also one way to do regularization, right? You only, you know, you only keep 700 neurons into the next layer, right? So let's, you know, reduce the dimension or reduce the complexity of your model. So this is, you know, a good way to do regularization as well. You can do, you know, 0.5 dropout, 0.3, or, you know, 0.3 dropout. something like that, right? So hopefully, you know, with this regularization and the dropout, right, we should control the complexity of the model. So yeah, it's a different name. Is it Keras? Yeah, actually. Oh, I didn't run this one. We load our, you know, functions first, right? The dropout layer and the regularizers, and then we call the functions. Right, so now this is a regularized model. Then we fit this model, maybe taking, you know, 1 minute or so, right? Let's see. So with, you know, this regularization, we should see, you know, this is improved, right? There's still some discrepancy, but it controls the complexity of the model. So the discrepancy is smaller, right? Should be smaller. Yeah, but you know what we know is that even with the, you know, even with regularization, this may still be a too complicated model, right? We not really need, you know, 1,000 neurons, but here's, you know, for illustration. Wait, why this didn't plot? Let me try again. Okay, yeah, I see. So essentially, you know, this model didn't converge, right? Did not give you like a very good, yeah, basically, you know, you can tell from the accuracy, not really converges. So this may not work. Yeah, let's change this back to maybe the L2 norm. That's, you know, less strict, probably. Anyways, so the point is, you know, with regularization, you should be able to account for overfitting, right? But sometimes, you know, may not be adequate if your initial model is too complicated, right? Essentially, right, this is not a good model, you know. You never want to do like 1,000 epochs for, you know, like a simple data set, right? Let's see if this works. Yeah. So now this, you know, it shows some improvements, right? But it's not still, you know, not ideal, right? So we might have, you know, less overfitting, but it may not be, you know, it's like a inferior model than the previous simple model that we fit, right? We should definitely prefer this, you know, previous model. So this is, you know, like a feed forward neural network example. Any questions before we, you know, we can look at the CNN example. Okay. So the next example is convolutional neural network. And this, yeah, so it does have the median post, right? And yeah, I think this should be, no, this one? No. Yeah, anyway, so I think you should be able to find like the GitHub, but like the code, right, it's used, but that's something, you know, you could check after class. So anyways, so for this data example, you know, we deal with image data from this CIFAR 10, right? This is the data set, you know, I mentioned to you. Essentially, it's, you know, the publicly available data set. Yeah, and then we always do this, right? You know, it's a public available data set where you essentially have 10 different categories for your images, okay? So we load this data set, and let's see, you know, we have a large number of training samples, right? 50,000 training samples and 10,000 testing samples. And this is the image size, right? So this image, they are actually compressed, you know, 32 by 32, and the dimension 3, right, corresponding to the, you know, the RGB coloring, right, the pixel coloring of your image. And in terms of the Y, right, because, you know, we know it is 10 categories, right? So essentially, you know, we have the class label, right, 1 through 10, or yeah, maybe it's 0 through 9, but anyways, right, it's 10 class labels. So if we, you know, directly, you know, print our X variable, X data, right? So X train 0 meaning, you know, like the first image, right? But, you know, we could, you know, print like our second image as well, right? But all of them, you know, they are matrix, like the 3-dimensional array, right? It's 32 by 32 by 3, you know, that's indicated here. And in order to see the image, right, essentially we need to do some conversion, and we use, you know, this plot function to show the image. You know, we see this is essentially the first image, right? You know, from human eye, you could kind of tell this is like a frog, right? And then the second image, you know, it's kind of like a truck, right? And you know, there are essentially 50,000 of them, right? This one is really, you know, blur because, you know, the image, they are compressed for storage, right? Anyways, so these are the images, and you know, we can also print the class label, right? Because, you know, for the training data, right, we know the class label. The label is for, I believe we have a correspondence. Yeah, maybe later. Yeah, this may be something like a deer, right, or something. So anyways, we will show the actual labels later, but you know, in our data, they are numeric labels, right? So anyways, you know, this is the data we have. Then we want, you know, for our CNN model, essentially, we want to build, right, our CNN model. So the first step is, right now we have our Y vector as, you know, a single vector, right? First thing is to convert it to Y1 through Y10. So each YK representing a class label, right? So we do this. And we see, you know, so we call this one hot encoding. You know, this is just a name, right? Which is basically convert a single vector into K vectors, right? And for the first, you know, sample, it's basically you take YK equal to 1 for the case class, right? And another one, right? You can see, you know, it is the this entry becomes 1, right? Another thing is, you know, we can also standardize or scale our input, right? Because they are RGB, you know, measures. So the maximum value is 255, right? So we standardize them to be, between 0 and 1 by dividing, the X matrix by 225. Now, in terms of building and training the CNN, right? So these are the, layers we have introduced: convolutional layer, pooling layer, dropout layer, right? We also mentioned. And then at the end, right, we want, fully connected layers, right, to do the output. So this is the same, functions that we call, right? We call these functions. So these are essentially the different layers, right? Dense layer. So dense layer corresponding to the fully connected layer, right? Dropout layer, flatten layer, convolutional layers. So there's like convolutional 2D, as well as, convolutional. So there's also, convolutional 1D or convolutional 3D, right? Based on the input shape of your data. And then max pooling layer as well, right? So there's also mean pooling or, median pooling, but most commonly people use max pooling. So
let me interrupt you. Someone has his hands up. Maybe they have a question to ask. I think
sure.
It's Azad.
It may be from, okay. It may be from the previous one, but.
Yeah,
From a
is
previous,
it like
okay.
you didn't lower your hand? I think, yeah, Azad had a previous question, right?
Okay, all right.
Yeah. But, yeah, let me know if you have a question. Okay, so here's, how we specify our model. So there's different ways, right? So previously we basically, write our model, write our layers directly in this sequential model, right? But another way is, we can add our layers one by one, right? This is not the right syntax. So I didn't run this. Yeah. So we start with an empty model, right? We just call this empty sequential model, and then use the model add, right, to add, subsequent layers. So a typical, convolutional layer looks like this, right? 32 meaning the number of filters actually we use. So, we want, a good amount of number of filters, right? So that it could extract, different information from the raw data. And yeah, 32, for example, or 16, etc., right? And this 3 by 3, this is the filter size, right? And activation, right? We all still need the activation function. ReLU would be, most commonly used. So padding is something we haven't seen before, right? But essentially, padding means, whether you move your filter outside of your, the boundary of your input image, right? So if you do not do padding, essentially, your filter starts from, for example, like the top left corner of your input, right? But with padding, essentially means, you could put your filter, like one step outside of the top left corner, right? So that's what we mean by padding. So that's kind of, you do not lose information at the boundary of your input image, okay? So, so this padding equal to same, meaning that after you apply your filter, your feature map, right? Your feature map has the same shape as your input image, right? Your input image is 32 by 32. So with padding, you keep the same 32 by 32 shape, after you apply the filter. Okay. So, then you can add additional convolutional layers, right? So actually, what the example here is that, you do not need to always, right, follow the convolutional layer by max pooling, but, you could do multiple convolutional layers and then do, for example, like a max pooling layer, right? So 32, you can change, these number of filters, right? For example, to 16 as well. And then you do the max pooling, and then, let's run this. Then you do, like a dropout, right? So once again, this dropout is for regularization, right? You do not want your model to be too complicated. And, you can print out your current model, right? The current model you specify. One thing to notice, right? Max pooling and dropout, they do not introduce additional parameters, right? Because they are just for dimension reduction. And the convolutional layers, even with 32 filters, you do not have like a too large number of parameters, okay? Then, you could add more layers, right? They're similar as before, right, with different, number of filters, essentially. And after adding the convolutional layers, right, you basically, you always want to call the flatten layer, before the fully connected, right, to basically convert your input shape to like a vector. So now we have, like additional dense layers that we specify. So for the output layer, right, because we have 10, different classes, so your output shape should be 10, right? And let's look at, at the end, what's the model we get. So this is, the final model structure. You see flatten, right, dense. So clearly, with the fully connected layer, it has the the most number of parameters, right? And so the total number of parameters, is over 2 million. That's typical, for neural network models, right? Oh, I mean, typical for convolutional neural network models, right? So, so similar as before, after we specify the model, we need to do, this model compile, specify the optimizer, right? Let's change it to Adam, just for illustration. And this training, might take some longer time. We can, try to have it run. So here I only specify 20 epochs, right? Because we have, 50,000 training samples, right? It will take some time to run. Okay, let's, just have this one running. And so this is, from like the previous plot, previous training, right? From the previous training, we see, this potential overfitting issue, right? So this means actually, your performance do not increase after 5 epochs also, right? And yeah, it's also, because our training data is really large in this case, right? And in terms of model accuracy, right? So, the validation accuracy did not improve after certain number of epochs. Yeah, we will, have this running. But let's look at, like the, like the model result, how it looks like, right? So this is from previous training, but the idea is the same, right? So this is the additional image we have, right? We just have this, you know, cute cat image that we want to do classification, right? First, we convert the image, you know, into the same shape, right, as our input image. It is blurred, right? Essentially, you know, a reduced quality, right? And then we call this model predict, right? So we use our fitted model, you know, to do the prediction on this additional image. And then we save the predicted probabilities here, right? You see here, you know, it's overwhelming probability of 0.9, right, to this category, right? And then we can, you know, map the numeric class labels, right, to the actual class labels here, right? So we see that the number 4 category is essentially cat, right? So we can, you know, print out our results. You know, it identifies the image as most likely to be a cat, right, with probability 0.9, and the dog, you know, has a probability of 0.09. That's the, you know, 2 overwhelming probabilities, right? For the other ones, it's really, you know, negligible probabilities. Yeah, so that's the end of the example. Let's see if the model, you know, finish running. Yeah, not yet, right? Yeah, anyways, yeah, I think we are out of time. So I want to, you know, stop here, and if we have any questions.
Yeah, so if you could please, it is really very great. Thanks so much. Then one thing I'll ask is if you could provide the code, because I was searching on the link you provided and I couldn't get into the code. So if you, since you have the IPython version, yeah, just if you could put it on the Slack or somewhere. But thanks. I'll pass it over to John. Thanks.
Yeah, I can, you know, like email you, you know, the code together with the slides. Yes.
Okay, sure. Thanks. And then copy John and the others just in case.
Yeah, definitely. Yeah.
Yeah. Thanks. Yeah.
So
yeah,
any
like
questions for Dr. Z? Questions, comments?
Someone find the GitHub link. Right? Yeah, so the author is Joseph Lee, right? Yeah, anyways, I'll share my code as well. Yeah.
Okay. And then just so, I mean, I don't be too much of it. So this also tells us that labeling the data, I mean, getting a good label for the data also goes a long way, right? So if, if the data is not labeled rightly, then of course, then your prediction goes out.
Yeah, totally. Yeah. For this example, you know, like all of your training samples, right? They should have the correct labels. Yeah, seems like the, you know, the training, the model is wrong. And we see, you know, this like the performance. And I can, you know, quickly show you. So this is evaluation on the testing. Overall, it's like 0.76 accuracy. You know, you could save your model, right? And I believe there's another, let's see. So there's a cat, right? Another cat example. We can take a look. So, you know, there's another cute kitten, and let's try to, you know, predict using our fitted model. And yeah, actually for this kitten, right, although cat is the top one, right, it has a 0.5 probability, you know, and the second one is dog with 0.35 probability. So you see the variation, right, in your prediction.
Thanks so much. Yeah, thanks.
Any more questions or comments for Dr. Z or anything in general? Yeah, so if there are no questions or comments, again, we want to thank Dr. Zifi. I mean, as all of you can see, I mean, he's not doing too well, but he was able to go through with all the flu and the cough. So we thank you so much for 2 weeks of a very great and informative presentation on statistical learning and predictive modules. Again, we all wish you a speedy recovery. Now, this is the last presentation for the fall training series. We had indicated before that to get the certificate, you have to complete any homework that the instructors give. So now that has been revised. So if you attended 5 of the 6 main training modules, you know, we started with the pre-training modules, and then we had the main module that started, I believe, with the classification module. So if you attended 5 of those, send email to VADSTI@howard.edu and then request your certificate. So there will also be a spring 2023 training series. Different topical areas will be presented, so you can look out for that as well. But before that, in November, in about 3 weeks, there will be a 2-day workshop on biodata catalyst. Biodata catalyst is an NIA tool that is a cloud-based data science ecosystem of tools and applications. So I'm sure you'll find that very interesting. So the announcement will go out, I believe, on Monday, or maybe within a few days after that. So you want to look out for that as well. Otherwise, thank you so much for your participation, because without your participation, this will not be great. So we thank you all for your participation, and then especially for those of you who started from the beginning and then all the way to the end. And then we thank all the instructors. If you are here, I mean, William is one of them. If there are any instructors on the Zoom, again, we thank you for your time and then all the very great and excellent presentations. So if anyone has any comments or anything to say, feel free to do so.
Then we'll also have Slack. So Slack will be there for forever. So if, at least for this module. So if you have any questions, you have the email address, you have Slack. I think there were mention of assignment. I've reached out to John and the instructors. We're going to try and compile them and put them in a single point where it will be easy for you to get to. So look out for that. Thanks so much.
Yeah, thanks all. It's my
Thank
pleasure,
you, everyone.
to have the opportunity. Yeah. All right. Yeah. So I'll send you email you some materials, and yeah. Thanks all.
Thank you.
And Dr. Kumar, thank you so much. I see you've been here almost through. Thank you very much.
Thank you for organizing things. I'm still learning, but I'll ask you other questions,
All right.
Thank
you.
Thank you.
All right. Yeah. Bye, everyone.
Hey, yeah, thanks, Dr. Bye-bye.
All right. So bye, everyone. And then all of you enjoy the rest of the day and then have a great weekend.